Hello students, welcome to Memoneet. This is Ravikant, your physics teacher, and the question paper which we are going to discuss today here is the question paper for BPT 8, which is of magnetic effect of current and magnetization, right? So the very first question we are going to discuss today here is the question number 1 says that a uniform magnetic field exists in a region by B is equals to 3I cap plus 4J cap plus 5K cap. A rod of length 5 meter placed along the y-axis is moved along x-axis with constant speed of 1 meter per second. The induced EMF in the rod is. So what they are saying that magnetic field is extended in a space, and the rod is being kept along y-axis. So the L vector for our formula will be equals to 5j cap, right? And it is moving with a velocity of 1 meter along x-axis. So our velocity vector v vector will be equals to I cap, right? The formula which we are going to use over here is induced EMF E is equals to v vector cross b vector, and the result of this will be dot producted with L vector. So first we find v vector cross b vector. So v vector is I cap is to be cross product with b, that is 3I cap plus 4j cap plus 5k cap. So I cross I is 0, I cross j is plus k, so it will give you 4k cap. I cross k is minus j, so will give you minus 5j cap. So this is v cross v. Now dot L. L vector is 5j cap, so 5j cap. So k dot j is 0 and j dot j is 1. So from here we get minus 25 volt, right? So the induced EMF will be 25 volts. The correct answer for this question is option 2, that is 25 volts. So this option 2 is the correct answer for this question, right? The formula which we have used in this question is E is equals to V vector cross B vector dot L vector, right? So the correct answer for this question is option 2. Now let's get into the question number 2. Question number 2 says that a 2 mega electron volt proton is moving perpendicular to a uniform magnetic field of 2.5 Tesla. The magnetic force on the proton is. So they are giving you a proton which has a kinetic energy of 2 mega electron volt, and it is moving perpendicular in a uniform magnetic field of 2.5 Tesla. We have to calculate magnetic force. The formula for the magnetic force is F is equals to Q V B sine theta, right? So charge of the particle, V is the velocity of the particle, B is the magnetic field, and theta is the angle between the V vector and B vector. So in this question, they have given us magnitude of the magnetic field, right? And they have given us the angle that it is moving perpendicular to the uniform magnetic field. Means the velocity and the uniform magnetic field are perpendicular to each other. It means theta is equals to 90 degree. But we do not have the value of V with us, but they have given us the kinetic energy. So the kinetic energy has the formula is equals to half mv square. So equating it with half mv square, that is 2 megavolt, when equated with half mv square will give you the energy. So if you look into the explanation, F is equals to QVV and E energy is equals to half mv square. From here we calculate the value of V and put into the formula, right? And then putting the values we get F is equals to 8 into 10 to the power of minus 12 Newton, right? So this is directly formula based question, that the formula we are using is F is equals to Q V B sine theta, putting theta as 90 degree, and using the formula kinetic energy is equals to half m v square. From here we find the value of B and put that value of B over here in this equation, and then putting the values, solving it, we get the force is equals to 8 into 10 to the power of minus 12 Newton. So the magnetic force experienced by a proton of energy 2 mega electron volts moving perpendicular to the uniform magnetic field of 2.5 Tesla is 8 into 10 to the power of minus 12 Newton, which is option 1. So the correct answer for question number 2 is option 1. Now let's get into the question number 3. The question number 3 says that a uniform magnetic field acts at right angle to the direction of the motion of an electron. As a result, the electron moves in a circular path of radius 2 centimeters. If the speed of the electron is doubled, the radius of the circular path will be. So if we explain the scenario over here, the scenario is that if this is the direction of velocity of the electron, then this is the direction of the magnetic field. That is, they are perpendicular to each other. This is B vector, right? And when this is the case, what will happen? The electron will move in a circular path. The electron will move in a circular path, and this circular path will have some radius. So the radius of the circular path is being given by the formula R is equals to mv by qb, where m is the mass of the particle, v is the velocity of the particle, q is the charge on the particle, and b is the magnetic field. So from here, what we can say that R is directly proportional to V, right? R is directly proportional to V. So in the question, they say that as a result, the electron moves a circular path of radius 2 centimeters. If the speed of the electron is doubled, that is, we are doubling the speed of the electron, that is, V is increasing 2 times. Therefore, the radius will also increase 2 times. So initial radius is 2 centimeters. So the final radius will be 2 times of 2 centimeters, which is equals to 4 centimeters. So the correct answer for question number 3 is option 3, that is 4 centimeters. So correct answer is option 3, that is 4 centimeter, right? R is equals to mv by qb. This is the formula which we are using over here. Now let's come to question number 4. Question number 4 says that which of the following particle will describe the smallest circle when projected with the same velocity perpendicular to the magnetic field. Again, the scenario is the same. Velocity and the magnetic field are perpendicular to each other. So the particle will undergo a circular motion, and that circular motion will have a radius of r is equals to mv by qb. And in the question, they say that all the 4 particles given in the option are being projected with the same velocity in the same magnetic field. Now let's check the charge on all the particles. Electron has a charge of E, proton again has a charge of E, helium plus again it has a charge of E, and lithium plus it also has a charge of E, right? So all the particles are having the same charge, so charge is also same. So from here we can say that R will be dependent on mass of the particle. So they are asking you the smallest circle. Smallest circle means smallest r. Smallest r means smallest mass. The least mass of among these 4, the electron has the least mass, right? So if electron has the least mass, so the smallest circle will be described by the electron. So according to this logic, the correct answer for this question number 4 is option 1. So the correct answer for question number 4 is option 1, right? Now let's get into next question. Your next question is question number 5. Question number 5 says a wire carrying current I is bent as shown in the figure and placed in a plane of uniform magnetic field B. The magnitude of the magnetic force experienced by the wire. So this is how the wire is being bent, and if the wire is bent in such a manner, then the length of the rod will be taken as, if suppose this we join these two ends, so this will be the effective length of the conductor. This will be the effective length of the conductor. It means we will be using this length as the length of the conductor instead of the entire length of the conductor, right? So the magnetic force has the formula F is equals to I cross I into L vector cross B vector, that is F is equals to IBL sine theta, right? So first we find the length of the effective length of the conductor. See, in this circle, this is r, this is r, and this we form a right angle triangle. So if I mark this end as A and this end as B, so the length AB will be equals to root 2 times of R, right? Because it is isosceles right angle triangle and the AB is the hypotenuse of that triangle. So the length of that triangle hypotenuse will be equals to root 2 times of R, right? The magnetic field is being given to us as B. So we will take the magnetic field as B. Now angle, what will be the angle? So if this is 90 and this is isosceles triangle, this angle will be 45. So this angle will also be 45. So we have theta as 45 over here, right? So we use the formula F is equals to I B L sine theta, right? Sine theta. So putting the values, we get F is equals to I is to be taken as I, B is to be taken as B, L is to be taken as root 2 R, and sine theta is sine 45, so it will be 1 upon root 2. So this root 2 and root 2 cancels out. We get F is equals to I B R, right? I B R. So the force experienced by this conductor will be equals to I B R. So let's take the option. So the correct option is I B R. So the correct option is option 3, I B R. So the correct answer for question number 5 is option 3, that is I B R. Now let's get into question number 6. Question number 6. Question number 6 says the direction of the magnetic force on a positive charge Q moving with a velocity v in a uniform magnetic field B for the following cases. So we are supposed to find the direction of the magnetic force. We are supposed to find the direction of the magnetic force for the two cases. The first case, the magnetic field is out of the plane. So we can draw it like this. Magnetic field is out of the plane means a dot of paper, and the velocity vector is eastwards. So velocity vector eastward means the directions which we follow is like this. This is north, this is east, this is east, right? And this is west and this is south. So what they say is, in the first case, the magnetic field is out of the plane of the paper and the velocity vector is eastward. So it is in this direction, right? This is the velocity vector. So velocity vector. So using the Fleming's left hand rule, what we'll get that if this is the magnetic field is coming out of the paper and velocity is in this direction, the force will be in downward direction. So we'll get force in downward direction. This will be the direction of the force. So this direction is nothing but south, right? And for the second case, it says that the magnetic field is directed towards south. Okay, so south is the magnetic field, and the velocity is in the southwest direction. Velocity is in southwest direction, right? So this is V. So in the formula we have F is equals to Q V B sine theta. So we move from V vector to V vector. While moving from V vector to V vector, we are moving in a anti-clockwise direction. So if we are moving in an anti-clockwise direction, the magnetic force will be in a direction perpendicular to paper and outwards, right? So in the first case, we have magnetic force in the south direction, and in the second case, we have the magnetic force out of the paper, or the plane of the paper. So this option is southwards, into the plane of the paper, no. Southwards, eastward, no. Southwards and out of the paper, right, right. So the correct answer for this question is option 3, that is, in the first case the magnetic force will act in the southward direction. In the second case, the magnetic force will act in the direction out of the plane of the paper, right? So I hope this solution is clear to all, because we have to visualize the directions. So the correct answer for question number 6 is option 3, right? Now let's get into question number 7. Question number 7. Question number 7, it says that if B1, B2, B3 and B4 are the magnetic field due to the current I1, I2, I3 and I4 respectively, then in Ampere circuitous law, closed integral B dot dl is equals to mu I. B is, see, in Ampere circuitous law, closed integral B dot dl will give you the flux, the net flux passing through the loop, and net flux passing through the loop is because of the net current enclosed inside the loop. Net current enclosed inside the loop. But the current here, this current here is the net current, but this B over here is the resultant magnitude of all the magnitude magnetic field, because of all the current present is around the loop. That is, whether the current is inside or outside, the magnetic field is inside or outside the loop, no matters, it is the net magnetic field. So basically over here, this B will be equals to B1 plus B2 plus B3 plus B4. So the correct answer will be option 3. Option 3 will be the correct answer for question number 7. Why? Because here I is the net current enclosed in the loop, passing through the loop, whereas B is the resultant magnetic field due to all current existing around the loop, that is, whether inside the loop or outside the loop. So we'll have to take the sum of all the magnetic fields. So it will be B is equals to B1 plus B2 plus B3 plus B4, right? So let's get into the next question. Is question number 8. Question number 8 says that a circular current loop of magnetic moment M is in an arbitrary orientation in an external magnetic field B. The work done to rotate the loop by 30 degree about an axis perpendicular to the plane is. See, if we are rotating a loop about its axis, rotating a loop about its axis would not change the angle between B vector and M vector. So there will be no work done. There will be no work done because there is no change in the angle. So there will be no work done in rotating the loop about its axis. So if there will be no work done, so the answer will be your option 4. Option 4 will be the correct answer. It is 0. See, we can understand it from this figure that initially this is the loop and this is the magnetic moment and this is the magnetic field. Both are along the axis. Now, if I rotate this loop by 30 degree about its axis, there will be no change in the direction or the angle between the M vector and B vector. They both will remain parallel, still they both remain the parallel. So if there is no change in the angle, if we follow this formula for work done, that is W is equals to MB cos theta 1 minus MB minus cos theta 2. Since there is no change in the angle between M and B vector, there will be no work done, and hence the answer for question number 8 will be 0 work done, that is option number 4, right? Now let's get into question number 9. Question number 9 says that a coil of 100 turns is lying in a magnetic field of 1 Tesla as shown in the figure. A current of 1 ampere is flowing through it. Then the torque acting on the coil will be. Torque for a coil inside the magnetic field, we have the formula tau is equals to mv sine theta, right? mv sine theta. And what is m? M is equals to nia, where n is the number of turn, I is the current in the conductor, the loop, and a is the area of cross section of the loop. B is the magnetic field in which the loop is being placed, and theta is the angle between the magnetic moment and the magnetic field, right? So putting the values here, we can see that tau is equals to ni ba sine theta. N is given as 100, current is I 1 ampere, and area of cross section is, sorry, n is 100, I is 1, b again is 1 Tesla, and the area of cross section is, area of cross section from here we can say area will be equals to 0.2 into 0.1, which will be equals to 0.02. So area of cross section is taken as 0.02 over here, and the direction between the angle between the m vector and b vector, the m vector will be perpendicularly outwards the plane of the paper, and b vector is from north to south, right? So the angle between them will be 90 degree, so sine 90. When we put this value and multiply, we get our torque is equals to 2 Newton meter. So the torque on the coil here will be equals to 2 Newton meter, which is in option 2. So the correct answer for this question is 2 Newton meter, which is option 2, right? Option 2 is the correct answer for question number 9. Now let's get into question number 10. Question number 10. Right. The power line lies along the east-west direction and carries a current of 10 ampere. The force per meter due to the Earth's magnetic field of 10 to the power of minus 4 Tesla is. See, if a wire, suppose this is the surface of the Earth and this is the wire going parallel to it. The magnetic field of the Earth has two components. One will be the horizontal component and one will be the vertical component, right? B vertical, right? Now they say that the wire is moving east-west in direction. So whether it is moving east to west direction or in any other direction, it will always remain parallel to the Earth's surface, right? So the angle between the current and the magnetic field vector over here is equals to 0 with the horizontal, but in case of the vertical component of the magnetic field of the Earth, it will be equals to 90 degree, right? So the force per meter due to the Earth's magnetic field, we have the formula F is equals to B I L sine theta, right? B I L sine theta. So for horizontal component, theta becomes 0 degree. So there will be no force because of this horizontal component. But for the vertical component, theta becomes 90 degree. So sine 90 is 1. So we'll put the vertical component, that is 10 to the power of minus 4. So putting the values in this, we put B as 10 to the power of minus 4 and I as current of 10 ampere. So 10, I will put I is equals to as 10, right? And then multiplying with L is equals to is 1 meter. L will be taken as 1 meter because they are asking the force per meter. So we'll take L is equals to 1 meter and putting the value, we'll multiply it. We'll get 10 to the power of minus 3 Newton. So force will be equals to 10 to the power of minus 3 Newton, which is in option 3. That is correct answer for question number 3 is question number 10 is option 3. Correct answer for question number 10 is option 3. Simply we have to put the values in the formula, that is F is equals to IBL sine theta. I is 10 amperes, B is 10 to the power of minus 4 Tesla, and L will be taken as 1, and theta is equals to 90 degrees, right? So now let's get into the question number 11. Question number 11 says, that a long straight hollow conductor tube carrying a current of two sections A and C of unequal cross sections joined by conical section B 1, 2 and 3 are the point on the line parallel to the axis of conductor. The magnetic field at 1, 2 and 3 have magnitude B1, B2 and B3. Then we have to find the relation between B1, B2 and 3. You see what they are saying, that this is a conductor. This is a conductor and this conductor has different cross-sectional area. At A it is having a smaller cross-sectional area and at C it is having a larger cross-sectional area. And these two different cross-sectional areas are connected with the help of a conical section B, right? And this tube, metallic tube is conducting current. So whenever a tube is conducting current, we assume that the entire current is flowing through the axis of the current, right? Axis of the current. Now if we assume that the entire current is flowing through the axis of the current, then the point 1, point 2 and point 3 are equidistant from this axis, and because they are equidistant from this axis, at all the 3 points, that is at point 1, point 2 and point 3, at all the 3 points will have the same magnetic field. So from here we conclude that B1 will be equals to B2 will be equals to B3. So according to this, the correct answer for question number 11 is option 1, that is B1 is equals to B2 is equals to B3. Again, why? Because for such a conductor which is a tube, whatever be the cross section, we assume that entire current is flowing through the axis of the tube, and the point where we have to calculate the magnetic field, that is point 1, point 2 and point 3, all the 3 points are equidistant from the axis, so all the 3 points will have the same magnetic field strength. Therefore, B1 is equals to B2 is equals to B3. So the correct answer for question number 11 is option 1. Right? Now let's get into question number 12. Question number 12 says Question number 12 says that a long solenoid of 200 turns per centimeter and carries current I, magnetic field at its axis is 6.28 into 10 to the power of minus 2 Weber per meter square. Another solenoid having 100 turns per centimeter and carries current I by 3, then the magnetic field at the axis will be. So there are two solenoids. First solenoid has a magnetic field of 6.28 into 10 to the power of minus 2. This is B. And B for a solenoid is equals to mu into N into I. So mu naught into N is 200 into I is I. Okay. Then the second solenoid, let it be B, the magnetic field in it will be B, is equals to mu naught, number of turns are 100, and the current is I by 3. So we have to calculate B. So dividing both the equations, what we'll get, mu naught cancels out with mu naught, this 100 cancels this 200, I cancels this I, and we get 3 over here. So what we are left with is 6.28 into 10 to the power of minus 2 upon B is equals to 3. So we'll get B is equals to 6.28 into 10 to the power of minus 2 upon 3. So this will be equals to no 3 and 3 to the 6. It will be equals to 6. What we are left here with into 2. This 2 is also left, right? So 2 into 3 is 6. So dividing this with 6 will get 1 point something. So it is 1.05. It is 1.05 into 10 to the power of minus 2 Weber per meter square. So according to this, the correct answer for this question is 1.05 10 to the power of minus 2. Option 2. So the correct answer for question number 12 is option 2, right? What we have done is simply we have written the equation using the formula, that is B is equals to, using this formula, that is B is equals to mu naught N I. B for the first solenoid has been given to us, mu naught is common for both the solenoids, N is 200 for the first solenoid and I is I. Again, writing for the second solenoid and dividing both the equations, we get B is equals to 1.05 into 10 to the power of minus 12 Weber per meter square, right? The correct answer is option 2 for question number 12. Now let's come into question number 13. Question number 13 says that it is a match the following. The first column has some laws and the mathematical expression for those laws are given in the column 2. So Biot-Savart law. Biot-Savart's law is your the fourth one. So this is for Biot-Savart law. Then the Ampere circuital law is closed integral B dot dl. So this is your for B, and then the force per unit length, this is mu naught I1 I2 upon 2 pi d. So this will be C, and then this will be D. So A is 1, so A is 4, B is 3, C is 1, and D is 2. So 4312. 4312. Yeah, it's in the first option itself. 4312. The correct answer for question number 13 is option number 1. 4312. Yeah. Option number 1. The correct answer is option number 1. Now let's get into question number 14. The question number 14 says that a uniform magnetic field of 1.5 Tesla exists in the cylindrical region of radius 10 centimeter. Its direction is parallel to the axis from east to west. A wire of length equal to diameter of the cylinder carrying current 5 ampere current in the north to south direction, alright, passes through this region. What is the magnitude and the direction of the force on the wire if the wire intersects the axis? So just to understand the scenario, if I draw the diagram, what we are going to take is we will be taking the reference of direction as uh, like this. This is north, this is east, this is west, and this is south. And as per the question, they say that uh, a uniform magnetic field of 1.5 Tesla exists in the cylinder region of radius of this. Its direction is parallel to the axis from east to west. So from east to west. So this is the direction of the magnetic field, and this is also the axis of the cylinder. So if I draw the cylinder, this is the cylinder, this is the magnetic field, and this is the axis of the cylinder. What they are saying is that there is a conductor of a wire of length equal to the diameter. So if radius is 10 centimeters, dia will be equals to 20 centimeters. So this is a wire of length 20 centimeter, has a current of 5 ampere current in the north to south direction. The direction of the current is, let me draw it like this, from north to south. This is the direction of current, right? This is the direction of current, this is the direction of magnetic field. They are asking you what is the magnitude and the direction of the force in the wire. So force is being given by the formula IBL sine theta. IBL sine theta. I is 5 amperes given to us, and B is 1.5 Tesla, and L is 20 centimeters, which will be equals to 0.2 meters, and theta is equals to 90 degree, as we can see from the diagram. So putting the values as I is 5 ampere, B as 1.5 Tesla, and L as 0.2 meters, and sine 90. We get the force as 1.5 Newton. So the magnitude is 1.5 Newton. So we have two options with that magnitude of 1.5 Newton. We need to find the direction as well. So either upward or downwards. So using the Fleming's left-hand rule, the magnetic field is in the east to west direction, right? And the current is this. So the force will be in the downward direction, that is into the plane of the paper. So we'll write it as downwards. So the option 3 is having the downward direction. So we have the correct answer for question number 14 as 1.5 Newton and downward direction. So the correct answer for question number 14 is option 3, right? Now let's get into question number 15. Let's get into question number 15. Question number 15. Now, question number 15 says that a closely wound solenoid of 2000 turns and area of cross section as 1.5 in 10 to the power of minus 4 meters square carries a current of 2 ampere. It is suspended through its center and perpendicular to its length, allowing it to turn in the horizontal plane in a uniform magnetic field of 5 into 10 to the power of minus 2 Tesla, making an angle of 30 degrees with the axis of the solenoid. The torque on the solenoid is. So, if solenoid is being suspended like this, then this is the direction of the magnetic field B, and this will be direction of the magnetic moment of the solenoid M, and the angle between them is equals to 30 degree. This is the scenario, right? So this is the scenario. So first we need to calculate M. So M will be equals to M. We can see here M is equals to NIA. N is 2000. I is 2 amperes. And A area of cross section is given as 1.5 10 to the power of minus 4. Calculating this, we get M is equals to 0.6 joule per Tesla, right? Joule per Tesla. And we know the formula for torque is equals to mb sine theta. B is being given to us as 5 into 10 to the power of minus 2 Tesla, and M we have calculated as 0.6 joule per Tesla, and theta here in question itself it is given that theta is equal to 30 degrees. So putting the values, M is equal to 0.6, B is equal to 5 into 10 to the power of minus 2, and cos 30 is 1 by 2. Solving this, we get torque as 1.5 into 10 to the power of minus 2 Newton meter. So the correct answer for this question will be 1.5 into 10 to the power of minus 2 Newton meter is an option 3, right? So the correct answer for this question is option 3. Correct answer for question number 15 is option 3. These are directly formula based questions. So if you remember the formula and you know how to apply the values, it could be done very easily, right? So if let's get into the question number 16. Question number 16 says a charged particle is projected in air horizontally near the earth's surface at a point where the horizontal component of the magnetic field is absent. Alright. Now considering the effect of the vertical component of the Earth's magnetic field and the gravitational field due to Earth, the path of the particle will be. Okay, so the scenario is that a particle is being projected like this. This is the velocity vector, and we have the magnetic vector perpendicular to it because we are having only vertical component, that is this is B vector of the Earth magnetic field. So because of this, it will go in the circular path. It will go under circular path, and this circle will be parallel to the earth surface, that is, it will be a horizontal circle, right? And this is because of the magnetic effect of the magnetic field of the earth. Now if we consider the gravitational field, the particle will be falling downwards, and the combined effect of the magnetic field and the gravitational field, what will happen, the particle will move in the circular path and gradually descend, and because of this it will form a helical path. As I'm showing you, it is undergoing circular motion also, and it is descending because of the gravity, right? So it will form a helical path. So the correct answer for this question number 16 will be option 2. The motion will be a helical motion, right? Now let's the correct answer for question number 13 is option 2. Question number 16 is option 2, right? Question number 16 has this correct answer is option 2. Now question number 17. Question number 17 says that a long hollow tube is carrying an electric current along its length distributed uniformly on its circumference. So we have already seen in the previous question also that if a tube is carrying a current, we assume that a entire current is flowing to the axis of the tube, right? They are asking you the magnetic field. They are asking about the magnetic field. So they are asking about the magnetic field. What they say, the increase linearly from the axis to the surface. No, it is constant inside the tube. Is zero only at the axis? Is zero just outside the tube? No. See, if this is the tube and this is the axis, and we assume that the current is flowing along this. So applying Ampere's circuital law from the axis to the circumference, there is no magnetic field. There is no magnetic field. So entire this region has zero magnetic field, right? So it will be a constant. It will be a constant value here, and it will have a maximum value of the magnetic field at the circumference, right? So according to this logic, the correct answer will be option 2, that it is constant inside the tube, right? Is zero only at the axis? No. And it is zero outside the exit tube? No, no, no. So the correct answer is option 2. The correct answer for question number 17 is option 2, right? Now let's see question number 18. Question number 18 is, it says pick out the wrong statement. Okay. The gain in the kinetic energy of the electron moving in a right angle to the magnetic field is zero. This statement is correct because again the scenario is, if the velocity is in this direction and magnetic field is in this direction, what will happen? Without changing the speed of the particle, it will just undergo a circular motion, that is, it will be a uniform circular motion. So if the magnitude of the velocity is not changing, the kinetic energy will also not change. Therefore, the gain in the kinetic energy will be zero. So this statement is correct. Now, when an electron is shot at right angle to the electric field, it traces a parabolic path. Right. This is also correct. We have studied in electrostats. Then the third option says an electron moving in the direction of the electric field gains kinetic energy. No. See, if this is the direction of electric field and the electron is also moving in the same direction, right? Electron is also moving in the same direction. What will happen? It will experience a force, a repulsive force. It will experience a repulsive force, and because of the repulsive force, it will experience retardation. And retardation means there is a decrease in the magnitude of the velocity. And if the magnitude of the velocity is decreasing, the kinetic energy will be lost instead of gaining. So this statement is wrong. Let's take the fourth statement also. An electron is at rest experiences no force in a uniform and constant magnetic field. This statement is also correct. So out of these four statements, we find that option 3 is a wrong statement and they are asking for a wrong statement. So the correct answer for question number 18 will be option 3, right? The correct answer is option 3. Okay. Now let's get into question number 19. Question number 19 says that two parallel conductors carrying current in the same direction attract each other, while two parallel beams of electron moving in the same direction repel each other. Which of the following statements cannot be the reason for this? The first statement says that the conductors are electrically neutral. Yes, electrically neutral. Okay. Now the conductors produce magnetic field to each other. Yes, this is the reason why they attract or repel. Now the electron beam do not produce magnetic field on each other. Yes, they do not produce magnetic field on each other. When an electron is moving, it produces a magnetic field and electric field both, out of which the electric field is dominating. Right? This is what they're saying in the fourth statement, I guess. They say the magnetic force caused by the electron beam on each other are weaker than the electrostatic force between them. Yes, right? So this is the reason, correct reason. This is also correct reason. So out of these four, all the four are the correct reason for the statement given in the question. So according to me, the correct option for this question has not been mentioned over here, right? Because the conductor are electrically neutral, and because they are electrically neutral and they experience the magnetic field of the other each other magnetic field of each other, they can be attracted or repelled according to the direction of the current, right? And the electron beams, they repel each other. Electron be moving in the same direction, repel each other. That is because of the electrostatic force, right? Electrostatic force, because the moving electron produces both magnetic field and electric field, right? So we don't have any answer for the question number 19. Let's see question number 20 then. Let's see question number 20. Question number 20, it says that the galvanometer consists of a coil with many turns wound on the cylindrical soft iron core. When a current flows through the coil, a torque acts on it, right? This torque is given as tau is equals to NIAB. Okay, the magnetic torque NIAB tends to rotate the coil at an angle of phi. The spring provides a counter torque phi F that balances the magnetic torque, right? The current sensitivity of the galvanometer is the deflection per unit current. Okay, deflection per unit current means more is the deflection per unit current, more will be the sensitivity. So the statement one says that two galvanometers with identical constructions but one with a core of greater permeability will have a sensitivity, lesser current sensitivity. Statement 2 says greater is the permeability of iron core, greater is the magnetic field. So statement 2 is correct, but what I find is statement 1 is wrong. Why? Because it says that two galvanometer with the identical construction but one with a core of greater permeability. If the permeability is greater, then the sensitivity will be more. Why? Because if greater is the permeability, greater will be the magnetic field, and greater is the magnetic field. Here, from here we can say greater is the magnetic field, the torque is directly proportional to the magnetic field, and if torque is more, deflection will be more, and deflection will be more, the sensitivity will be more. But they are saying that the sensitivity will be less. So the statement first is wrong and statement 2 is correct. Let's see the option, what the option says. The first option says that statement 1 is true. No. Second option says the statement 1 is true. Again, it's not correct. Statement 3 says statement 1 is true. No. Statement 4 says statement 1 is false and statement 2 is true. Alright. So the correct answer for question number 20 will be option 4. that is statement 1 is false and statement 2 is true. So if a core is having a greater permeability, then the sensitivity of the galvanometer will increase. Why? Because if greater permeability, then the iron core will have greater magnetic field, and greater is the magnetic field, greater will be torque. Greater is the torque, greater will be the deflection, and more is the deflection per unit current, more is the sensitivity of the galvanometer. So the correct answer for question number 20 is option number 4. Now let's see question number 21. Question number 21. Okay. It says that the nature of parallel and anti-parallel currents are: parallel current repel and anti-parallel current attract. Second option says parallel current attract and anti-parallel current repel. Third says both current attracts. Fourth says both current repel. No. Simply we have studied the derivations, that force per unit length on the conductors, and this diagram also clarifies that if the currents are in the same direction for two different conductors, the force between them is an attractive force. For the same direction, that is when the current is parallel, the force is attractive, and when the current is anti-parallel, the force is repulsive. So according to that, the correct option for question number 21 is option 2. So the correct answer for question number 21 is option 2, that is the parallel current attract and the anti-parallel current repel. Right? Now question number 22. Question number 22 says a field is shown in the figure. Right? The field cannot represent. The field is a circular field, is a loop. So loop can be represented by a magnetic field. Loop does not represent the electrostatic field because electrostatic field never closes. It originates from positive charge and it terminates in negative charge. Right? So it never forms a loop. Then induced electric field. Yes, induced electric field can be a loop. All of these no. So the correct answer for this question is field cannot represent. So option 2 is the correct answer. Right? Question number 22 has its correct answer as option 2 because this loop could not represent an electrostatic field. Now question number 23. Question number 23 says that if a long hollow copper pipe carries a direct current, the magnetic field associated with the current will be only inside the pipe, only outside the pipe, neither inside nor outside the pipe, both inside and outside the pipe. We have already seen earlier using Ampere circuital law that inside the pipe the net current encloses 0, right? Because all the current is flowing in the circumference. So net current encloses 0, therefore there will be no magnetic field. So it's only inside, no, only outside. Yes, only outside. So the correct answer for question number 23 is option 2. That is only outside. The magnetic field is only outside. Now let's see question number 24. Question number 24 says that a straight section PQ of a circuit lies along the x-axis from x is equals to minus a by 2 to x is equals to plus a by 2 and carries a steady current I. The magnetic field due to the section PQ at point x is equals to plus a will be. Okay, so this arrangement is shown in this diagram that this is y-axis, this is x-axis, and we have the straight section PQ placed on the x-axis as x, one of this end at x is equals to minus a by 2 and other end at x is equals to a by 2. Right? They are asking us the magnetic field due to this PQ at point M, that is at x is equals to a, that is on the axis of this straight conductor or straight section of the circuit. So on the axis of the circuit, the magnetic field is 0. The magnetic field is 0. At the axis, the magnetic field is 0. So the correct answer for this question is option 4, that is the magnetic field is 0. So correct answer for question number 24 is option 4. Right? Now let's get into question number 25. Question number 25 says that a moving coil sensitive galvanometer gives at once much more deflection. To control its speed of deflection, a high resistance is to be connected across the terminal. No. A magnet should be placed near the coil. Yes. A small copper wire should be connected across its terminal. No. The body of galvanometer should be earth. No, the correct answer is option 2, that is by keeping a magnet close to the coil, it will give a damping magnetic field. It will work as a damping magnetic field and it will reduce the deflection, and the deflection will be in control. So the correct answer for question number 25 is option 2. Right. Now let's get into question number 26. From here we get into the magnetism. The first, the magnetism, question number 26 says, question number 26 Question number 26 says a circular loop of flexible conducting material is kept in a magnetic field directed perpendicular into the plane. Alright, the magnetic fields are into the plane. By holding the loop at a diametrically opposite point, it is suddenly stretched outwards. Then, see, if we are stretching this loop outwards, what will happen? The area of cross section will decrease. So we have phi, that is the flux passing through area, is equals to B dot dA, right? And if B dot dA is reducing, the flux will reduce, right? And flux is reducing, so we have induced EMF is equals to minus d phi by dt. So if the flux is changing, EMF will be induced, and according to Lenz's law, if whatever be the cause of the induced EMF, it will be opposed, right? It will be opposed. So what is the cause here? Cause here is the reducing EMF, reducing flux. So we have the current induced should be in such a way that it increases the flux. To increase the flux, we have to increase the magnetic field, because we are decreasing the area. So magnetic field is to be increased. So to increase the magnetic field, we need more magnetic field lines getting into the plane of the paper. So to get magnetic field line inside the paper, the direction of the current should be in a clockwise direction, right? The direction of the current should be in the clockwise direction. Let's see the options. The first option says no current is induced in the loop. No current is induced because the area is changing, flux is changing. Second, anti-clockwise current is induced. No. Clockwise current is induced. Yes. Only EMF is induced. No. So option 3 is correct. Option 3 is the correct answer for question number 26. That is, a clockwise current is being induced when we stretch the loop diametrically opposite, in the opposite direction, right? Now let's see question number 27. Question number 27 says that magnetic accessibility of a diamagnetic substance is, just you have to remember it, that it is very small and is negative. For a diamagnetic substance, the accessibility is small and is negative. So the correct answer is option 4, the diamagnetic. Yes. So correct answer for question number 27 is option 4. Next, again it's a memory based question. Question number 28. Question number 28 says that the ratio of the magnetic length to geometric length of a bar magnet is about, we have to memorize it, that it is equals to 0.84. So the correct answer for question number 28 is option 2, that is it is 0.84. What the ratio of the magnetic length to the geometric length of a bar magnet is about 0.84. Now let's get into question number 29. Question number 29 says that a magnetic field is produced and directed along y-axis. Magnetic field is along y-axis. So your B vector is along J cap. A magnetic needle is placed along x-axis. It means it will have its magnetic dipole moment along x-axis, that is along I cap. The direction of the torque on the magnet will be, so torque is given as tau is equals to m vector cross, torque is equals to m vector cross b vector. So m vector cross b vector means I cross j. So I cross j is equals to k cap. So k cap means in the positive z direction. So the torque will be in the positive z axis. So the correct answer is in xy plane along y axis, along z axis, torque will be 0. No. The correct answer is option 3. That is question number 29 has an answer as option 3. That is, the torque will be along z axis. Simply vectors, cross product of vector quantities. Question number 30. For which among the following the magnetic accessibility does not depend on the temperature? So the magnetic accessibility does not depend on temperature is for diamagnetic substances. right? So the correct, again you have to remember it. It's a property of diamagnetic substance that it does not depend on the temperature. So question number 30 has its correct answer as option number 4. That is diamagnetic substances, their susceptibility, magnetic susceptibility does not depend on the temperature. Now question number 31. Question number 31 says that the combination of the two bar magnets make 20 oscillations. Okay, 20 oscillations per minute in a oscillation magnometer when like poles are tied together, and 5 oscillations per minute when unlike poles are tied together. The ratio of the magnetic moment B. So when the like poles are tied together, the net magnetic moment would be, let it be M1 plus M2, where M1 is the magnetic moment of the first magnet and M2 will be the second magnet. And when this is the case, let's take the frequency as F1, and this is equals to, they have given as 20 hertz, right? And when the case that unlike poles are tied together, the net magnetic moment will be M1 minus M2 because the opposite poles are tied together. And for this case, the frequency is for unlike like poles are tied together and 5 oscillations per minute for unlike poles. So frequency F2 is equals to 5 hertz, right? And we know the relation that F, frequency of oscillation, is directly proportional to under root of M. So from here we can say that F1 upon F2 is equals to under root of M1 plus M2 upon M1 minus M2, right? It will be M1 minus M2, M1 minus M2, right? Now putting the values and solving it, we can see it from here that, or we write it here. F1 is 20, right? F1 is 20, F2 is 5, and this is equals to under root of M1 plus M2 upon M1 minus M2. Squaring both the sides will get, this is equals to 4, so we'll get 16 is equals to M1 plus M2 upon M1 minus M2, and then we'll apply componendo and dividendo over here. We'll get M1 upon M2 as, here we'll get M1 upon, applying componendo dividendo, that is from the ratio and proportion, right? We will get M1 upon M2 as 17 upon 15. We will get M1 upon M2 as 17 upon 15. So the correct answer is 17 upon 15, option 2, right? So the correct answer for question number 31 is option 2. Componendo dividendo means numerator plus denominator upon numerator minus denominator, right? So this for left right hand side you will get 2m1 upon 2m2, and for left hand side you will get 17 upon 15, and this 2 and 2 goes off, we'll get m1 upon m2 as 17 upon 15. Componendo and dividendo is numerator plus denominator upon numerator minus denominator, right? On both the sides of the equation. Then question number 31 is done. Option 2 is the correct answer. Question number 32. Question number 32. It says which of the following statement is incorrect. So the first statement says the magnet does not exert a force on a stationary electrically charged body. This is correct. We need incorrect. Magnetic field lines are closed continuous curves and extends from south pole to north pole within the magnet. This is again correct. Then the tangent of the magnetic field line at any point gives the direction or the magnetic field at that point. This is also correct. Fourth statement says the magnetic field lines are widely separated where the magnetic field is strong. No, this is wrong, because wherever the field is strong, the magnetic field lines are, or any vector field is close to each other. The field lines for any vector field, if it is strong, the field lines will be very close to each other, whether it is electric field or magnetic field or gravitational field. So here for the case of magnetic field, if the field is strong, the field line should be very close to each other. They are saying, but here they are saying that it's widely separated. So this statement is wrong. So the correct answer for question number 32, as they need an incorrect statement. So the correct answer is option 4. Option 4, that the fourth statement is an incorrect statement, right? So now let's get into question number 33. Yeah. Question number 33. Question number 33 says that the magnetic simple a paramagnetic sample shows net magnetization of 18 ampere per meter, all right, when placed in an external magnetic field of 0.9 Tesla at a temperature of 36 Kelvin. When the same sample is placed in an external magnetic field of 0.3 Tesla at temperature of 54 Kelvin, the magnetization will be. See, the paramagnetic material magnetization is given as M is equals to CB upon T, where C is the Curie's constant. So here we have M is equals to CB upon T. So from here we can say that M is directly proportional to B and inversely proportional to T, and from there we can write that M1 upon M2 is equals to B1 upon B2 into T2 upon T1. So we have the values of B1 as 0.9 and T1 as 36 Kelvin, B2 as 0.3 Tesla and T2 as 54 Tesla, and we have M1 as 18. Putting all the values over here and calculating for M2, we get M2 as 4 ampere per meter. So the correct answer for this question number 33 is 4 ampere per meter. That is option 1. So option 1 is the correct answer for question number 31. Simply remembering the formula, that is M is equals to CB by T, and applying the proportionalities over here and putting the value, we get M2 is equals to 4 ampere per meter, right? So now let's get into question number 34. Question number 34 says, question number 34, right? Question number 34 says a very small bar magnet is placed in the magnetic meridian with its south pole pointing towards north. The null point is obtained 20 centimeter away from the center of the magnet. If the Earth's magnetic field horizontal component at the point B 0.3 Gauss, the magnetic moment of the bar magnet is. So the scenario is explained in this diagram. This is the north-south direction, and the south of the magnet is placed in the north and the north is placed in the south, and we are having a null point N2 and N1 which are at 20 centimeters from the center of the magnet, right? So for this we have the magnetic field is given as B is equals to 2m upon r cube, where r is the distance of the null point from the center of the magnet. So putting the values over here, B is being given to us as 0.3 Gauss, right? And we need to calculate M, and R is being given as 20 centimeters. So we need to calculate in the CJ system only. So we do not have to convert this 20 centimeters into meters. Putting the values and calculating, we get our M is equals to 1.2 into 10 to the power of 3 EMUs, right? So we are using the formula here is B is equals to 2m upon r cube, where B is the magnetic field, M is the magnetic moment which we need to calculate, and R is the distance of the null point from the center of the magnet. Putting the values, we get M is equals to 1.2 into 10 to the power of 3 EMU, right? So the correct answer for question number 34 is option 1.2 10 to the power of option 2, right? The correct answer for question number 34 is option 2. Now let's get into question number 35. Question number 35 says Xi1 and Xi2 are susceptibility of paramagnetic material of a temperature T1 and T2 respectively. Then, so relation between Xi and T is Xi is inversely proportional to T. So we can say Xi1 into T1 is equals to Xi2 into T2. So this we have in option 2. So the correct answer for question number 35 is option 2, right? So let's see question number 36. Question number 36. Okay. Question number 36 says that closed integral b dot ds is equals to 0. That is, this is Gauss law in magnetism. So what this says that if this is a closed loop, a closed surface, and I place a magnet inside it, right? This is, let's say, south pole, and this is, let's say, north pole. So because the magnetic field lines form a loop, right, the net field lines exiting the loop will be equal to the number of field lines entering the loop. So the net flux passing through this loop will be equal to 0, right? So the magnetic flux will be 0, that is closed integral B dot ds will be equals to 0, right? So the what they say here is, first option is total magnetic field due to the magnet is 0, right? No, not due to the magnet is 0. No, the net magnetic field due to the magnet is not 0. It has some value because of the magnet. Now the net magnetic flux through Gaussian surface for a magnetic field is equal to 0. Yes, the net flux is 0. So this is correct. Now the magnetic monopole do not exist. So this is also correct, right? So the magnetic monopole does not exist. So according to this, the correct answer will be option 3. That is, magnetic monopole does not exist. This is the conclusion that we got from here. That magnetic monopole. Magnetic monopole means a magnet with a single pole, that is an only north pole. So that is not possible, right? If this could happen, then this could have a non-zero value, right? So what we conclude from here is that option number 30, question number 36 has a correct answer as option number 3. Correct answer is option 3, right? So question number 37, which among the following have negative susceptibility? Negative susceptibility is for diamagnetic substances, and among these the diamagnetic substance is bismuth. Again, you have to remember the properties. So the correct answer for question number 37 is option 3. Now question number 38. Question number 38 says that which of the following relation is not correct. So this is correct. This is correct. This is incorrect, right? Because the relation here which is written should be, it is mu is equals to mu naught into 1 plus xi, right? Or we also write mu r, that is relative permeability, is equals to 1 plus xi, right? 1 plus xi. So according to this, the wrong relation is option 3. Rest all the relations are correct because, yes, all the relations are correct. So the correct answer for question number 38 is option number 3. Now question number 39. Question number 39 says that the tape recorder records the sound in the form of, so the tape recorder has a magnetic strips, right? And the electrical signals were sent into it because of those particles on the magnetic strip got magnetized, and the data was being stored in the form of magnetic field on the tape. So the correct answer for this question number 39 is option 4, that the data was being stored in the form of, or the tape was recorded the sound in the form of magnetic field on the tape. So the correct answer for question number 39 is option 4. Now let's get into question number 40. Question number 40 says that if a magnetic material moves from stronger to weaker part of the magnetic field, then it is known as a diamagnetic material. Why diamagnetic material? Because when a diamagnetic material is placed in a external magnetic field, it gets magnetized in the opposite direction. So it has a tendency of moving from a weaker part to, from stronger part to the weaker part, right? So the correct answer for this question number 40 is option 3, that is a diamagnetic material. When placed in an external magnetic field, it moves from a stronger to weaker part of the magnetic field. So the correct answer for question number 40 is option 3, right? Option 3. Next question number 41. 41 says when a magnetic substance is heated, it loses its magnetization. Yes. Remains the same? No, no chance of remaining same. Loses its magnetization? Yes. Becomes stronger? No. Either 1 or 3? No. Option 2. When you beat or deform a magnet, or if you heat a magnet, it will lose its magnetization. So correct answer for 41 is option 2. Now the question number 41 is option 2. Question number 42. The liquid oxygen remains suspended between the two pole faces of the magnet because it's paramagnetic in nature, right? Oxygen, liquid oxygen or oxygen is paramagnetic in nature, so it is attracted by the north pole and the south pole. Both the poles attracted, and it remains suspended between the poles. So the liquid oxygen remains suspended between the two pole faces of the magnet because it is paramagnetic in nature. So the correct answer for question number 42 is option 2, that is oxygen is paramagnetic in nature, and this is the reason for its suspension between the two poles. Now let's get into the question number 43. Question 43 says that an iron magnet cannot retain its magnetism when it is melted. Iron metal has a temperature greater than its Curie temperature. Yes, both the statements are correct, and it's the correct explanation because the melting point of iron is so high that it exceeds its Curie temperature, and once its Curie temperature has been exceeded, it cannot retain its magnetic property, right? So that is what they are saying, that an iron bar magnet cannot retain its magnetism when it is melted, because when it will be melted, the temperature will go beyond the Curie temperature and it will lose its magnetism, and that is what they have written in the reason that iron melt at a temperature greater than the Curie temperature. So first statement and the second statement are correct, and the second statement is the correct explanation for assertion. So the I hope the correct answer is option number 1, that is if both assertion and reason are true and the reason is the correct explanation for the assertion, right? So the correct option is 1, right? Both assertion and reason are true but reason is not correct. Assertion true but reason false. Assertion and reason both are false. Assertion for different. So correct answer is option number 4. So correct answer for question number 43 is option 1. That is assertion and reason both are true, and reason is the correct explanation for assertion. Let's come to question number 44. 44 says if a magnet of pole strength M is cut into 4 parts such that the length and width of each part is half that of initial one, then the pole strength of each part will be. Okay, see what has been done is, suppose this is a bar magnet. If I cut this bar magnet like this, the pole strength will not change. What by cutting it like this, what we have done is length is made half. What else we have to do? We have to make the width half. So we are getting 4 pieces over here. Now this is let's say area of cross section becomes half. Now when area of cross section becomes half, in this case the pole strength will reduce by half, means it will become half. So every part will have its pole strength as if it was initially m, finally it will be m by 2. So the correct answer for question number 44 is option 4, that is m by 2. Right, cutting the magnet in this manner, that is along the width, we are reducing the length. When we reduce the length, the magnetic pole does not change, but when we change the width, that area of cross section, the magnetic strength will change, magnetic pole strength will change. So because we are making it half, so the magnetic pole strength M will change to half, so it will be M by 2. The correct answer for question number 44 is option number 4. Now let's come into question number 45. Question number 45 says unit of magnetic successibility is. Magnetic successibility is a unitless or dimensionless quantity. So it has none of these, right? Because magnetic successibility is equals to m upon h, and both has the unit as ampere per meter, right? So ampere per meter and ampere per meter cancels out and we get no unit. So this is a dimensionless quantity. So the correct answer for question number 45 is option number 4. Now question number 46. Question number 46. Question number 46 says that relative permeability means mu r of iron is this, then the magnetic susceptibility is. So mu r is given as mu r is equals to 1 plus xi. 1 plus xi. So they are asking you xi. So simply 5 5500 is equals to 1 plus xi. So xi is equals to 5500 minus 1. 5500 minus 1 is 5499. 5499 is option 3. So correct answer for question 46 is option 3. Right? Yes. 5499 simply using the formula. Now question number 47. The ferromagnetic material is placed in an external magnetic field. Ferromagnetic material is placed in an external magnetic field. The magnetic domain will increase and decrease both depending on the how it is being placed, right? When a ferromagnetic substance is placed in an external magnetic field, the size of the domain lying in the direction of the external magnetic field will increase, while the size of the domain lying in opposite direction, it will decrease. So it will both increase and decrease depending upon how it is being placed. So the correct answer for this question is option may increase or decrease. Option 3, right? Option 3 is the correct answer. So option 3 is the correct answer for question number 47. Question number 48. Which of the following statements are correct? Magnetic field lines can be entirely confined within the core of a toroid. The magnetic field lines can be entirely confined in the core of solenoid. A bar magnet exerts a torque on itself due to its own wheel. ये तो बिल्कुल गलत है. This is absolutely wrong. And a system can have a magnetic moment even though its net charge is zero. Magnetic moment is nowhere dependent on the charge. This is wrong. This is correct. We have more than one statement correct now. So magnetic field lines can be entirely confined within the core of the solenoid. No, because it comes out of the solenoid. With that only we have. So this is also wrong. For toroid, yes, toroid it is inside the core itself. So option A is also correct and D is also correct. So if A and D are correct, we have option 2 as the correct answer. See, when a toroid is a loop, right? It is like this, and the magnetic fields are within it, right? The magnetic fields are within it, inside. There is no magnetic field outside. There is no magnetic field here. There is no magnetic field here for a toroid. But when it comes to a solenoid, suppose this is the solenoid, right? So the magnetic field will be like this. So they are coming outside the core, right? Magnetic field, suppose it's in this direction, so it is coming out of the core. But in case of the toroid, it's not out of the core; it remains inside the core. So according to this, the magnetic field lines be entirely confined within the core of a toroid. This is correct. But the magnetic field line can be entirely confined within the core of solenoid. No, this is not correct, because we can see it is coming out of the core, and the bar magnet they itself cannot exert a torque on itself. So this is again also wrong. And option D, a system can have a magnetic moment even though its net charge is zero. This is also correct. So option statement A and statement D both are correct. So the correct answer for question number 48 is option 2. That is only A and D are correct. Right. Now let's see question number 49. Question number 49. They are given as a hysteresis loop. Figure shows the magnetic hysteresis loop that is the BH curve of a ferromagnetic material. Select the correct statement. The correct statement for this is the value of B at H is equals to 0 is called coercivity. No, it's not coercivity. B at H is equals to 0. B at H is equals to 0 is known as remanence. This is known as remanence. Alright, so this is wrong. We need the correct statement. An electromagnet has a low remanence and low coercivity. This is correct. The value of H and C, the value of H at C is called remancivity. Value of H at C is known as, no, it is known as coercivity. This is known as coercivity. So this is again is wrong. Fourth statement. Fourth statement says that the permanent magnet has low remissivity and low coercivity. No, it has high remissivity. It will be high, and this also be high, right? So again, this statement is also wrong. So permanent magnet has high remissivity and high coercivity. They are giving it as low, so this is wrong. Value of H at C is known as coercivity. So this statement is also wrong because they have written as remissivity. The value of B at H is equal to 0 is called coercivity. This is also wrong because this is known as remissivity. Remanence. So the correct answer is option 2, that is the electromagnets have low remanence and low coercivity. The correct answer for question number 49 is option 2. Right? Now, question number 50, the last question of this question paper. It says that assertion is when radius of a circular loop carrying current is doubled, its magnetic moment becomes 4 times. Magnetic moment I is M is equals to NIA, right? So A is pi r square. So if we double the radius, area will become 4 times, right? And that's what they are saying. When the radius of the circular loop carrying current is double, its magnetic moment becomes 4 times. So if area becomes 4 times, magnetic moment will also become 4 times. Statement assertion is correct. Magnetic moment depends on the area of the loop. Yes, it depends on the area of the loop. So statement assertion is correct, reason is correct, and reason is the correct explanation of assertion. So option 1, that both assertion and reason are true, and the reason is the correct explanation of the assertion. True but not correct. False, false, false. So the correct answer for question number 50 is option 1, right? Because M is equals to NIA and A is equals to pi r square. So according to this, if radius is doubled, area will become 4 times, and because area and magnetic moment are directly proportional to each other, so if area increases 4 times, magnetic moment will also increase 4 times. So the correct answer for question number 50 is option number 1, right? I hope the explanation for the entire question paper is clear to all. If there is, right? So that is all for this question paper. Thank you.